In the mid-1990s, time on the Hubble Space Telescope was perhaps the most precious commodity in the scientific world. Astronomers spent years refining proposals, battling for mere minutes of observation, justifying every second of the telescope's attention with rigorous mathematics and predicted outcomes. The machine was a finite resource, a singular eye that could only look at one thing at a time. To turn it toward a specific star or galaxy was an investment. To turn it toward nothing was viewed by many as a dereliction of duty. Yet, this was precisely the proposal that began to form in the mind of Robert Williams, the director of the Space Telescope Science Institute. He possessed a rare currency known as director's discretionary time, a fraction of the telescope's schedule that he could allocate without the usual peer review or bureaucratic approval. He decided to spend this currency on a gamble that defied the standard logic of astronomy. The prevailing method of science is hypothesis-driven. You observe a phenomenon because you have a theory about it, or you target an object because you know it exists and wish to understand its properties. Williams proposed the opposite. He wanted to point the most powerful telescope in history at a patch of sky that ground-based surveys had declared completely empty. He wanted to stare into the void, not because he knew what was there, but specifically because he did not. It was a decision to prioritize discovery over confirmation, to embrace the risk of finding absolutely nothing in exchange for the slim possibility of seeing the unseen. The criticism was immediate and sharp. If the image came back black, it would be a public failure for a telescope that had only recently been redeemed from its initial optical flaws. It was a high-stakes wager played out in the silent vacuum of low Earth orbit. The first challenge was not capturing the image, but finding the right kind of nothing. The sky is crowded with local distractions that can ruin a deep view of the universe. The team needed a corridor of darkness, a narrow tunnel through the debris of our own neighborhood. They had to avoid the bright, scattered light of our solar system's dust, known as zodiacal light. They had to bypass the teeming billions of stars in our own Milky Way galaxy, which stand in the foreground like dirt on a window pane. They needed a keyhole that looked out of the galactic plane into the intergalactic deep. After an exhaustive search, they identified a tiny region in the constellation Ursa Major, near the handle of the Big Dipper. To the naked eye, and even to standard telescopes, it was a blank canvasser, nondescript patch of darkness covering an area of the sky roughly equivalent to a grain of sand held at arm's length. Securing the target was only the beginning of the logistical complexity. To see the faintest objects in the universe, the telescope could not simply snap a photograph. It had to collect light like a bucket collects rain during a drought. The objects they hoped to find were likely billions of times fainter than what the human eye could perceive. Capturing them required an exposure time not measured in fractions of a second, but in hours and days. This meant the telescope had to remain locked on that single, invisible grain of sand while orbiting the Earth at 17,000 miles per hour. It had to compensate for the shudder of its own machinery, the thermal expansion and contraction caused by passing from sunlight into shadow, and the gravitational tug of the planet beneath it. The precision required was akin to holding a laser pointer steady on a dime located hundreds of miles away, and maintaining that steadiness for nearly 2 weeks. The observation began in the final days of 1995, as humanity below turned its attention to holiday festivities and the turning of the calendar. The telescope began its silent vigil. For 10 consecutive days, spanning from December 18th to the 28th, Hubble stared at the dark spot in Ursa Major. It was a tedious, repetitive process. The telescope would take an exposure typically lasting between 15 to 40 minutes, soaking up whatever stray photons happened to be traversing that corridor of space. Then, as its orbit took it through the South Atlantic anomaly, a region of intense radiation, the instruments would pause to protect the data, only to resume the stare once clear. Over the course of those 10 days, the telescope executed this maneuver 342 times, layering image upon image, adding the faint signal of one exposure to the next. There is a profound stillness to this kind of exploration. We often imagine discovery as a dramatic, loud event, a shout in a laboratory or a blast off a launch pad. But here, discovery was an act of accumulation. It was the passive reception of light that had been traveling since before the Earth existed. These photons had journeyed across the expanding fabric of space, undisturbed for billions of years, only to end their existence by striking the chilled sensors of a CCD camera suspended above our atmosphere. Each photon was a messenger from an epoch that had long since vanished, carrying the spectral signature of stars that may have burned out while our solar system was still a cloud of formless gas. The telescope did not reach out. It waited. It allowed the universe to come to it, drop by drop, filling the digital well with information that no human mind had yet processed. During the observation, the data was meaningless to the casual observer. It arrived as raw binary code, a stream of numbers representing intensity and position, transmitted via radio waves to tracking stations on the ground. There was no instant Polaroid, no immediate confirmation that the gamble had paid off. The astronomers were effectively flying blind, trusting the mathematics of the exposure times and the stability of the gyroscopes. The fear remained that the patch was truly empty, or that the background glow of the universe would wash out the faint signals they sought. It was a period of suspended judgment, a technological meditation on the unknown. The team had to trust that the laws of physics remained consistent across the deep gulfs of time they were attempting to bridge. As the hundreds of separate exposures were linked, the process of assembly began. This was not merely stacking photographs. It was a complex restoration project. Cosmic rays, high-energy particles zipping through space, had peppered the images with bright, full streaks that had to be mathematically subtracted. The alignment of the separate frames had to be perfect to ensure that a smudge of light on one frame overlapped exactly with the same smudge on the next, reinforcing the signal while the random noise of the background cancelled itself out. It was a digital excavation, brushing away the static of the immediate environment to reveal the fossils buried underneath. The work was slow, methodical, and quiet, taking place in glowing monitor rooms rather than the cold vacuum where the data was born. The philosophical weight of the endeavor began to settle on the team even before the final image was complete. They were conscious of the fact that they were drilling a core sample into the history of the cosmos. In geology, digging down reveals the strata of previous eras. In astronomy, looking out is looking back. By targeting a region devoid of nearby stars, they were effectively looking down a long, unobstructed hallway into the nursery of the universe. The light they were catching had left its source when the universe was young, traversing a cosmos that was smaller, hotter, and denser than the one we inhabit today. They were not just taking a picture of a place, they were taking a picture of a time. The emptiness of the chosen field was the very quality that allowed for this temporal depth. It was the lack of foreground that made the background accessible. This concept of looking back creates a vertigo unique to astronomy. We are accustomed to seeing things as they are in the present moment. When we look at a mountain, we see the mountain as it exists now. But in the deep field, the now is an illusion. The farther away an object is, the older the image we receive. The telescope was acting as a time machine, but one with a strict limitation. It could only view the past, never influence it. The sheer scale of the distance meant that the view was decoupled from the reality of the present. The galaxies they hoped to see might have collided, merged, or faded into darkness eons ago. But the news of their fate had not yet reached Earth. The telescope was capturing ghosts, the lingering afterimages of grand structures that obeyed the speed limit of light. As the processing neared completion, the disparate frames of red, blue, and green light were ready to be combined into a single color representation. The anxiety of the empty sky began to dissolve, replaced by a growing realization of what had been caught in the trap. The raw data hinted at density. The numbers suggested that the black square was not black at all, but textured. The silence of the vacuum had been deceptive. Where the human eye saw a void, the long exposure had revealed a crowded, chaotic tapestry. The decision to stare at nothing was about to fundamentally alter the human perspective on everything. To ask what lies in the darkness is to challenge the oldest instinct of the living mind. For as long as we have possessed consciousness, we have defined our reality by presence. We measure the world by the solidity of the ground beneath our feet, the warmth of the sun on our skin, and the visible shapes that populate the horizon. We trust what reflects light. When the light fades, or when the shapes dissolve into the expansive black of night, our intuition tells us that reality has thinned. We naturally equate the absence of visibility with the absence of existence. If we cannot see it, we assume it is not there. This is not merely a failure of vision. It is a protective mechanism, a cognitive shield that allowed our ancestors to make sense of a dangerous world, where the unknown was often synonymous with the lethal. This equation of darkness with emptiness is woven into the very language we use to describe the universe. We speak of the void of space, a word that stems from roots, meaning vacant or unoccupied. We talk of the vacuum, implying a state of absolute nothingness, a sterile jar from which all substance has been sucked away. Even in our most poetic moments, we describe the night sky as a canvas, a passive black backdrop that exists solely to highlight the brilliance of the stars. In this view, the stars are the actors, and the darkness is merely the stage, silent, static, and fundamentally empty. We look up and see the points of light as the only things that matter, the islands of being in an ocean of non-being. However, this perception is a deception of scale and a limitation of biology. Our eyes evolved near a yellow star, on a planet flooded with sunlight, adapted to navigate a world of medium-sized objects moving at medium speeds. We are creatures of the day, designed to hunt and gather in the clarity of illumination. When we look into the deep shadows, our retinas struggle, sending only static to the brain. Because the brain abhors a lack of data, it interprets this lack as a void. We project our sensory limitations onto the cosmos itself, assuming that because we see nothing, nothing exists. But the universe is under no obligation to conform to the narrow bandwidth of human vision. History is filled with examples of this same error, where the edge of perception was mistaken for the edge of the world. There was a time when the horizon of the ocean was believed to be the absolute end of the earth. To the coastal cultures standing on the shore, looking out at the great heaving line where water met sky, there was nothing beyond. The ocean was not seen as a bridge to other lands, but as a barrier of negation. It was the great limit. Maps from antiquity often left these areas blank, or filled them with the warning, terra incognita, unknown land, or fanciful illustrations of sea monsters. These monsters were not born of observation, but of psychology. They were the manifestations of our fear of the empty. We filled the silence with roaring beasts because a hostile presence was easier to comprehend than an indifferent nothingness. The same logic applied to the forests that bordered early settlements, or the caves that plunged deep into the earth. Darkness was the realm of spirits, of the dead, of things that did not belong to the world of the living. To enter the dark was to step out of the ordered cosmos and into chaos. This primal association lingers. When we look at the gaps between the stars, we feel a similar, ancient hesitation. It is the vertigo of looking over a cliff, not into a valley, but into a bottomless drop. The blackness of space feels like a subtraction of reality, a place where the rules of existence might fray and snap. Yet, throughout the centuries, there were always those who suspected that the darkness was hiding something. As our tools improved, the empty spaces on our maps began to fill. The blank ocean proved to be teeming with currents, islands, and entire civilizations unknown to the observer on the shore. The dark forests were revealed to be complex ecosystems, rich with life that simply operated on a different rhythm than the village. The lesson repeated itself over and over. Absence of evidence is not evidence of absence. Every time humanity pushed a sensor, a ship, or a probe into a supposed void, we found that the void was crowded. In the realm of astronomy, this lesson took longer to learn because the distances are so vast and the darkness so profound. For thousands of years, the study of the heavens was strictly the study of bright things. Astronomers charted the movements of planets, the cycles of the moon, and the fixed positions of the brightest stars. The space between them was ignored, treated as the necessary spacing that kept celestial bodies apart. It was the silence between the notes, having no value of its own. Even as telescopes grew larger, their primary purpose was to make bright objects brighter, to resolve the fuzzy patches of nebulae, or to split binary stars. The darkness itself remained a blind spot, not because it was invisible, but because it was deemed uninteresting. This dismissal of the dark overlooks a fundamental truth about the nature of light itself. Light is a traveler. It carries information across the gulf of space, but it also obscures. A bright object dominates the view, washing out the fainter, subtler signals that lie behind or beside it. The glare of a nearby star can hide an orbiting planet. The brilliance of a galaxy's core can outshine the ancient, dimmer stars on its periphery. In this way, light can be a veil. It captures our attention and holds it hostage, preventing us from seeing the deeper textures of the universe. To truly see, one must sometimes look away from the light. Consider the air in a room. To the naked eye, it appears clear and empty. We move through it without resistance, regarding it as nothing. Yet, we know it is a dense soup of nitrogen, oxygen, argon, and dust, vibrating with thermal energy, carrying sound waves and radio frequencies. If we could switch our eyes to see the microscopic or the electromagnetic, the empty air would become a blindingly chaotic storm of activity. The vacuum of space is similar, though far more subtle. It is not a true void. It is a fabric, stretched and warped by gravity, threaded with magnetic fields, and awash in a sea of particles that pop in and out of existence. The shift in understanding began when we realized that darkness is not a passive state, but a container. It is the medium through which the history of the universe flows. Just as the ocean holds the memory of every storm and every current, the dark sky holds the faint, stretched light of the very first epoch of creation. These signals are there, arriving constantly, raining down on Earth from every direction. They pass through our roofs, our bodies, and the Earth itself. We do not feel them, and we do not see them, but they are as real as the ground we stand on. The problem has never been that the universe is empty. The problem is that our bucket is too small to catch the rain. We are now approaching a moment in our narrative where the definition of seeing had to be rewritten. To explore the true nature of this emptiness, humanity had to build a mechanical eye that did not blink, an eye that could stare into the abyss without fear or boredom. But before we could build the machine, we had to build the philosophy that justified it. We had to accept that looking at nothing was a valid scientific pursuit. This required a shedding of ego. It required admitting that the bright, obvious landmarks we had navigated by for millennia were perhaps not the main structure of the universe, but merely the foam on top of a deep, dark sea. This realization did not happen overnight. It was a slow dawn, a gradual accumulation of anomalies and questions that the old model of a bright universe could not answer. Why were the galaxies moving apart? What was pushing them? Why did the outer edges of spiral galaxies spin as fast as the inner core, defying the laws of gravity as we understood them? The visible matter, the shining stars and glowing gas was not enough to explain the motion of the cosmos. The math implied that there was more, vastly more, hidden in the shadows. The darkness was heavy. It had mass. It had influence. It was pulling the strings of the visible world, a silent puppeteer whose presence could only be inferred by the dance of the puppets. We wake up in a world that feels whole. When we open our eyes, the room floods with color and shape. The morning light strikes the wall, the sound of wind filters through the glass, and the floor feels solid beneath our weight. It is an experience of seamless continuity. We do not feel as though we are missing anything. The picture of reality presented to us by our senses appears complete, extending from the tips of our fingers to the furthest horizon. We move through our days with the quiet confidence that what we see is what exists, and that our perception is a transparent glass through which the true nature of the universe flows. But this feeling of completeness is perhaps the most convincing illusion our biology has ever constructed. The human body is not a general-purpose instrument designed to investigate the cosmos. It is a biological vessel shaped by millions of years of specific, terrestrial requirements. We are creatures of the surface, evolved to survive in a narrow layer of atmosphere, under the light of a single, stable yellow star. Our senses were forged in the crucible of immediate survival. We needed to spot the ripe fruit against the green leaf, to hear the snap of a twig that betrayed a predator, and to feel the shift in temperature that heralded a storm. We did not need to see the atomic structure of the air we breathed, nor did we need to hear the radio waves pulsing from distant galaxies. To possess such senses would have been not a gift, but a distraction, a chaotic flood of useless data that would have paralyzed our ancestors. Therefore, evolution acted as an editor. It trimmed away the excess. It tuned our sensory dials to the precise frequencies required to keep us alive on Earth, and it muted everything else. The eye, which we rely on as our primary anchor to truth, is in reality a highly restrictive filter. It is sensitive to a sliver of the electromagnetic spectrum so thin that, if the entire spectrum were stretched out as a road extending from New York to Los Angeles, the visible light we can see would amount to a few inches of pavement. Within those few inches lies every color, every sunset, every face, and every star we have ever witnessed with the naked eye. On either side of that narrow strip lies a vast, invisible country of gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves all flowing through us and around us at every moment, completely undetected. This limitation means that we are effectively walking through a crowded room while wearing a blindfold that has only a tiny pinhole pricked through the center. We see the beam of light that passes through the hole, and we construct our entire understanding of the room based on that single beam. We assume the rest of the room is empty or silent, simply because our equipment cannot register it. If our eyes were tuned to radio waves instead of visible light, the day sky would not be blue. It would be a chaotic, glowing tapestry of signals from communication satellites, distant pulsar, and the leftover heat of the Big Bang. If we could see gravity, the empty space around the Earth would look like a heavy, curved fabric. Our definition of reality is strictly determined by the hardware we were born with. The deception runs deeper than just the spectrum of light. It extends to the way our brains process the signals they do receive. The act of seeing is not a passive recording, like a camera snapping a photo. It is an active construction project. The eye captures raw, inverted, and often shaky data, which travels along the optic nerve to the visual cortex. There, in the silent darkness of the skull, the brain assembles a model. It stabilizes the image, corrects the colors based on lighting conditions, and fills in the blind spots where the optic nerve connects to the retina. What we experience as sight is a prediction, a best-guess simulation of the world, rendered milliseconds after the physical event has actually occurred. We are always living slightly in the past, viewing a delayed broadcast of our own lives. This biological lag is imperceptible in the rhythm of a normal day. When we pour a cup of coffee, the delay between the liquid hitting the cup and our brain registering the event is irrelevant. But when we look up at the cosmos, the limitations of our internal clock become a profound barrier. We intuitively understand the world in terms of human seconds, human hours, and human lifetimes. We possess a gut feeling for the size of a rock, the height of a tree, or the distance to the next town. These are scales that fit within our hands or our stride. But the universe operates on scales that our intuition cannot grasp. When we speak of the distance to the moon, or the sun, or the nearest star, the numbers slide off the surface of our minds. We can say 93 million miles, but we cannot feel it. The human brain, having evolved to navigate landscapes measured in walking days, creates a mental shortcut. It compresses the vastness into a flat backdrop. The stars look like they are all resting on the same ceiling, equidistant and small. We have no sensory depth perception for the galaxy. A star that is 10 light-years away and a star that is 10,000 light-years away appear as identical points of light to the naked eye. The true, terrifying depth of the void is flattened into a harmless wallpaper. We look at the night sky and feel a sense of peace, largely because we are biologically incapable of seeing the violent, churning distances that actually separate those points of light. This mismatch between our sensory tools and the reality of the universe creates a persistent false impression of stillness. To the human eye, the heavens appear static. Apart from the slow drift of the moon and planets, nothing seems to change. A star seen tonight will be there tomorrow, and likely when our grandchildren look up. This stability suggests a universe that is calm, eternal, and unchanging. But this, too, is a trick of our narrow window. If our eyes could perceive time differently, if we could watch the sky with the patience of a mountain or the speed of a high-frequency camera, the stillness would vanish. We would see stars spinning at impossible speeds, gas clouds collapsing and igniting, and galaxies colliding in slow motion, ballets that span millions of years. The violence and the energy are there. We simply lack the temporal bandwidth to register them. Our sense of touch, too, is a localized phenomenon that fails us in the wider cosmos. We define solid by the resistance of electrons repelling each other in the atoms of our fingertips and the object we touch. We feel the table as a continuous, hard surface. Yet, physics tells us that the table is almost entirely empty space, a lattice of tiny particles suspended in a void, held together by invisible forces. If we were the size of a neutrino, we could pass through the Earth without ever striking an atom. Our sensation of solidity is a macroscopic illusion, a convenient summary of atomic forces that allows us to interact with the world without falling through the floor. In the deep vacuum of space, where matter is spread so thin that a single atom might be miles from its neighbor, our concept of touch loses all meaning. We are also trapped by the bias of medium. We live in a pressurized fluid atmosphere. Sound is our constant companion, the vibration of air molecules carrying information to our ears. We associate activity with noise. A busy street is loud, a quiet room is still. We instinctively expect the universe to follow this rule. We imagine that a supernova explosion must roar, or that the collision of two planets would crack like thunder. But space is a vacuum. It is the realm of silence. The most violent events in existence occur without a sound. This silence feels unnatural to us, adding to the sensation that space is dead or empty. We equate the lack of acoustic feedback with a lack of presence. Yet the energy released in those silent events could incinerate our entire solar system. These limitations, the narrow spectrum of light, the compression of distance, the illusion of solidity, and the dependency on air for sound create a boundary around human experience. We live inside a sensory bubble. Within this bubble, the laws of physics seem intuitive, and the world makes sense. We can throw a ball and predict its arc. We can shout and expect an echo. But as we move our attention outward, to the domain of the very large and the very far, the bubble becomes a prison. Our natural intuition begins to fail. The tools that helped us survive on the savannah become liabilities when we try to understand the curvature of spacetime or the nature of black holes. The history of astronomy is, in many ways, the history of realizing that our senses are liars. It is the story of discovering that the sun does not revolve around us, even though it feels like it does. It is the realization that the ground is not stationary, even though it feels steady. It is the acceptance that the solid world is mostly empty space, and the empty space is filled with invisible fields. We have had to learn to distrust our own perceptions, to use mathematics and machinery to see what our eyes cannot. We have had to accept that the world, as it appears to us, is only a user-friendly interface, a simplified dashboard that hides the complex engine underneath. As we stand on the threshold of deep exploration, we must acknowledge that our biological equipment is insufficient. We are trying to read a library of books written in a language we do not speak, using eyes that can only see the covers. The universe is not hiding from us. It is simply broadcasting on frequencies we were not built to receive. To understand the message, we must stop relying on the equipment we were born with and start relying on the extensions we can build. We must trade the intuition of the hunter-gatherer for the abstraction of the physicist. We must be willing to accept that reality is far stranger, far louder, and far more crowded than our quiet, dark nights would suggest. When we strike a match in a dark room, the flame illuminates the walls instantly. The delay between the spark and the sight of the room is so infinitesimally small that our minds perceive it as simultaneous. Cause and effect appear to happen in the same breath. This immediacy trains us to think of light as a condition of the environment, a mere quality of presence that allows us to navigate. We think of light as something that simply is, but in the vast theater of the cosmos, light is not a passive condition. It is an active traveler. It is a physical entity that must cross the void, mile by mile, carrying its burden of information across distances that defy comprehension. To understand the universe, we must stop thinking of light as brightness and start thinking of it as a courier, a solitary messenger, bringing news from a time and place we can never visit. This shift in perspective transforms the night sky from a static picture into a ceaseless flow of mail. Every star we see is a sender, broadcasting its story into the vacuum. Once a photon, a single packet of light, breaks free from the churning surface of a star, it is entirely on its own. It is decoupled from its source. The star that birthed it might collapse, explode, or fade into a cold cinder. But the light it sent continues to travel, indifferent to the fate of its parent. It speeds through the silence of interstellar space, preserving the image of the star exactly as it was at the moment of departure. It is a message in a bottle cast into the largest ocean imaginable, drifting for eons until it finally crashes against the retina of an observer or the glass of a lens. The journey of this light is governed by the strict, unyielding speed limit of the universe, while light is the fastest thing in existence, moving at roughly 186,000 miles per second. The cosmos is so large that this speed can feel like a crawl. On the scale of a room, light is instant. On the scale of the solar system, it is sluggish, taking 8 minutes to travel from the sun to the Earth. On the scale of the galaxy, it is glacial, taking 100,000 years to cross from one edge of the Milky Way to the other. And on the scale of the deep universe, light is a slow-moving historian. This delay is the fundamental mechanism that allows us to understand our origins. Because light takes time to travel, looking out into space is literally looking back in time. We never see the universe as it is now. We see it as it was. This reality turns the sky into a deep archive. The moon we see is a second and a half old. The sun is an 8-minute-old memory. The nearest star is a ghost from 4 years ago. The Andromeda Galaxy, a smudge of light visible to the naked eye on a clear night, is an image 2.5 million years old. We are seeing that galaxy not as it exists today, but as it existed when early humans were just beginning to craft stone tools. The light from that galaxy has been traveling through the emptiness for the entirety of human history, arriving only tonight. The deeper we look, the further back we go. The universe has preserved its own infancy in these traveling beams, keeping the record of its evolution alive in the transit of photons. But light carries more than just an image of the past. It carries a detailed biography of its source. If we treat light merely as illumination, we miss the dense code hidden within it. To the unassisted eye, starlight appears white or slightly tinted blue, yellow, or red. This color is the first layer of information, a rough indication of temperature. Just as a piece of iron glows red when hot and blue-white when scorching, a star reveals its surface heat through its color. A red star is a cooling ember. A blue star is a raging furnace. This simple visual cue allows astronomers to take the temperature of an object trillions of miles away without ever touching it. The light acts as a thermometer, preserving the thermal state of the star across the cold void. However, the true language of the universe is written in a script much finer than simple color. If we unravel the beam of light, spreading it out like a fan, we discover that it is not a solid ribbon of white, but a complex barcode. This is the science of spectroscopy, but in the context of our story, it is the art of reading the signature. Every element in the universe, hydrogen, helium, carbon, oxygen, interacts with light in a unique way. When light passes through a cloud of gas, or bubbles up from the core of a star, the atoms of those elements leave their fingerprints on the beam. They absorb specific frequencies, leaving behind tiny dark gaps in the spectrum, or they emit specific colors, adding bright lines to the pattern. These spectral lines are the DNA of the cosmos. They tell us what the universe is made of. By analyzing the light from a distant star, we can determine that it contains iron in its atmosphere, or that a nebula is rich in oxygen. We can detect the presence of water vapor on a planet orbiting another sun, simply by studying the faint, filtered light that survives the journey. This is a staggering realization. We do not need to send a probe to a star to sample its chemistry. The star sends the sample to us. It broadcasts its composition in the very light it emits. The universe is constantly shouting its ingredients into the void, waiting for someone with the right prism to read the recipe. This information is preserved with miraculous fidelity. A photon created by a calcium atom in a distant galaxy carries the exact same signature as a photon created by a calcium atom in a laboratory on Earth. The laws of physics are consistent across the span of space and time. This consistency allows us to build a bridge of understanding between the here and the there. We can look at a smudge of light from the edge of the observable universe and know, with certainty, that it contains the same building blocks that make up our own bodies. The light is a universal courier, translating the alien environment of the deep cosmos into a language of elements that we understand perfectly. The fidelity of this signal is maintained by the very emptiness of space that we often fear. If the universe were filled with a thick fog or a dense atmosphere, the light would be scattered, absorbed, and lost. The message would be garbled before it could travel more than a few miles. But the vacuum of space, for all its hostility to life, is the perfect medium for memory. It allows light to travel for billions of years without degrading. The darkness preserves the light. It protects the integrity of the signal, allowing the faint pulse of a dying galaxy to cross the abyss and arrive at Earth with its story intact. The emptiness we perceive is not a waste of space. It is the necessary clear channel for the transmission of history. As we stand on the Earth and look up, we are immersed in this silent conversation. The air around us is filled with these intersecting lines of sight, a web of signals crossing from every direction. Most of these signals pass us by, striking the ground and vanishing, their stories unread. But when we turn our attention upward, when we decide to catch the light and analyze it, we are engaging in an act of cosmic listening. We are decoding the memoirs of ancient giants. The universe is not silent. It is merely speaking in a language of frequency and wavelength, a language that requires no sound, only the patient accumulation of photons. As we delve deeper into this language, we begin to realize that the visible light, the rainbow of colors our eyes can see, is only a tiny fraction of the vocabulary. The universe does not stop communicating just because our eyes stop seeing. There are energies too high for our retinas to handle, and waves too long for our biological sensors to register. The story of the universe is being told on 1,000 different channels simultaneously, and for most of human history, we have been tuned into only one. There is a gentle irony in the relationship between life on Earth and the view of the universe. The very blanket of air that allows us to breathe, that protects us from the harsh radiation of the sun, and keeps our water from boiling away into space, is the same veil that blinds us to the deeper cosmos. We live at the bottom of a deep ocean of gas. We move through it, breathe it, and depend on it. But for the astronomer, this ocean is a turbulent, distorting lens. For thousands of years, humanity looked up from the floor of this ocean, trying to decipher the shapes on the surface, unaware that the medium through which they looked was fundamentally altering the message. The atmosphere is not a static piece of glass. It is a living, moving fluid, churned by the heat of the sun and the rotation of the planet. It is composed of layers of varying temperatures and densities, constantly mixing and colliding. When a beam of starlight which has traveled in a perfectly straight line for millions of years hits the upper atmosphere, its journey of precision ends. It begins to stumble. As it passes through pockets of warm air and cold air, the light is refracted, bent slightly this way and that, thousands of times a second. To the human eye, this chaotic dance creates the romantic twinkling of the stars. We perceive it as a gentle shimmering, a sign of the night's beauty. But to a telescope, this twinkling is a disaster. It smears the sharp point of a star into a fuzzy, dancing blob. It erases fine detail, blurring the separation between close objects and washing out the faint structures of distant galaxies. This atmospheric turbulence acts as a hard limit on what can be seen from the ground. No matter how large the mirror or how perfectly polished the glass, a telescope on the Earth's surface is always looking through a moving haze. It is akin to trying to read a book submerged at the bottom of a swimming pool while the surface is being pelted by rain. You can see the book, you can tell it is there, but the words are constantly shifting, breaking apart, and reforming in unintelligible shapes. For centuries, astronomers fought this battle by building their observatories on the tops of the highest mountains, climbing above the thickest, wettest layers of the air. There, the sky is darker and the air is thinner, offering moments of stillness known as good seeing. But even on the highest peak, the atmosphere is still there, a thin curtain that never fully lifts. Beyond the blurring, the atmosphere imposes a second, more severe limitation: censorship. The air is an effective shield, designed by nature to block harmful energy. The ozone layer absorbs ultraviolet light. Water vapor absorbs infrared. Gamma rays and X-rays are stopped dead in the upper strata. This is fortunate for the survival of DNA, which would be shredded by high-energy radiation. But it is catastrophic for a complete understanding of the universe. Celestial objects do not emit light only in the colors we can see. Violent events like black hole accretions scream in X-ray. The birth of new stars happens inside dust clouds that only glow in the infrared. By staying on the ground, we are deaf to more than half of the universe's conversation. We are trying to understand a symphony while only being able to hear the violins, missing the drums, the horns, and the deep resonance of the cellos. The realization that the ground was a trap grew slowly. It became clear that to truly see, we had to leave. The dream of a space telescope was born not from a desire for adventure, but from a desperate need for clarity. It was a vision of an instrument liberated from the weather, floating in the eternal stillness of the vacuum. In space, there is no air to shimmer. There is no wind to shake the frame. There is no day to interrupt the observation. For in the shadow of the Earth, the sky is permanently black. A telescope in orbit could see the universe as it truly is, sharp, steady, and unfiltered. It could capture the full spectrum of light, from the deepest infrared to the harshest ultraviolet, opening a window that had been nailed shut since the formation of the Earth's atmosphere. However, the leap from the mountaintop to the orbit was not merely a matter of altitude. It was a fundamental shift in the relationship between the observer and the instrument. On Earth, a telescope is a tactile thing. The astronomer is there. They can adjust the focus with a hand, replace a faulty fuse, or simply look through the eyepiece to check the alignment. The machine is a companion, accessible and repairable. To place a telescope in space is to exile it. It means building a machine that must survive on its own, hundreds of miles above the nearest human hand. It must operate in a vacuum where lubricants freeze and metals weld themselves together. It must draw its power from the sun and point itself with a precision that defies mechanical friction. This requirement for autonomy changed the nature of the engineering. The instrument could not just be a magnifying glass, it had to be a spacecraft. It needed a brain to process commands, a radio to scream its findings back to the ground, and a thermal system to keep its delicate mirrors from warping in the alternating freeze of the shadow and the roast of the sun. The concept challenged the very definition of what an observatory was. It was no longer a building with a dome. It was a satellite, a robotic island of science drifting through the silence. The psychological barrier was just as high as the technological one. It required trusting a machine to be our eyes in a place where we could not go, to act as a proxy for human curiosity in the hostile dark. The drive to build such an eye began long before the technology existed to launch it. It started as equations on chalkboards and papers published in obscure journals, speculative dreams of a time when rockets would be more than weapons of war. It was a patient ambition, waiting for the space age to catch up with the imagination of the astronomers. They knew that as long as they remained on the surface, they were merely skimming the top of the data. The profound questions, how old is the universe? How fast is it expanding? Are we alone? Lay hidden behind the atmospheric veil. To answer them, they had to rise above the air. This necessity stripped the romance of space travel down to its utilitarian core. The goal was not to plant a flag or leave a footprint, but to park a camera in the stillness. It was a humble objective in the grand scheme of exploration, yet it promised a greater return than any physical journey. A human explorer can only see what is in front of them, but a space telescope can see almost everything, everywhere. It can stare at a single patch of nothingness for days on end, accumulating light that no human retina could ever register. It can act as a time machine, effectively bypassing the limitations of biology and geography. As the plans for this great observatory began to solidify, the focus turned to the nature of the mirror. In the absence of air, the sharpness of the image would be limited only by the quality of the glass. On Earth, a perfect mirror is wasted because the air ruins the image before it hits the glass. In space, the mirror becomes the ultimate limit. It had to be ground to a perfection that was previously thought impossible. If the mirror were the size of the Earth, the largest bump on its surface could be no taller than a few inches. It had to be smoothed down to the wavelength of light itself. This demand for perfection was not vanity. It was the mathematical requirement of the vacuum. In the clarity of space, every flaw is revealed. There is no atmosphere to hide behind, no blur to mask an imperfection. The instrument had to be as perfect as the view it sought to capture. The transition from the ground to the sky represents a shedding of weight. It is the story of humanity finally putting down the heavy burden of the atmosphere. We had carried this visual static for our entire existence, accepting the twinkling stars and the blue sky as the absolute reality. We did not know what we were missing until we theorized what lay beyond the interference. The decision to build eyes beyond Earth was a declaration that we were done with the blurry version of the truth. We were ready to see the sharp edges of creation, even if it meant looking at a universe that was stranger and colder than the one we saw from our gardens. The history of exploration is rarely a straight line of triumphs. It is a jagged path of delays, miscalculations, and the quiet, crushing weight of unmet expectations. For decades, the idea of a large space telescope had existed as a shimmering promise in the minds of astronomers. It was the ultimate machine, the device that would finally lift the veil of the atmosphere and allow humanity to see the universe with absolute clarity. The planning had consumed careers. The engineering had pushed the boundaries of what was physically possible. By the spring of 1990, the waiting was over. The Hubble Space Telescope, a school bus-sized cylinder of silver foil and precision glass, sat atop the launch pad, ready to ascend. It was not just a scientific instrument. It was a symbol of technical infallibility, a testament to the belief that if humans built something with enough care and money, it would work perfectly. On April 24, 1990, the Space Shuttle Discovery roared into the Florida sky, carrying the telescope in its cargo bay. The ascent was flawless. The shuttle pierced the atmosphere that had frustrated astronomers for centuries, reaching the silent calm of low Earth orbit. The deployment was a delicate ballet of robotics and physics. The shuttle's arm lifted the massive observatory from the bay and held it against the backdrop of the Earth, a shining, metallic object suspended between the blue curve of the planet and the black depth of space. The solar panels unfurled like the wings of a golden insect, drinking in the sunlight to power the computers and heaters. Then, the grip was released. the telescope drifted free, a solitary island of glass and electronics, embarking on its mission to capture the light of the beginning of time. Down on the ground, the mood was one of held breath. The control centers were filled with the quiet tension of engineers who knew that their work was now beyond their reach. There is a profound helplessness in space. Once the object is in orbit, it is untouchable. You cannot walk up to it and tighten a screw or wipe a lens. You can only send commands via radio waves and hope the machine listens. For the first few weeks, the news was good. The systems came online. The spacecraft stabilized. The door protecting the mirror opened, exposing the glass to the starlight. The team prepared for first light, the ceremonial first image that would prove the telescope's power. They expected a revelation. They expected a picture so sharp it would make every ground-based photograph look like a rough sketch. The first image arrived on May 20th. It was a picture of a star cluster, a standard target for calibration. As the data formed into a picture on the monitors, a silence fell over the room that was not the silence of awe, but of confusion. The image was better than what ground telescopes could achieve. Yes, but it was not the crystal-clear pinpoint they had been promised. The stars were not sharp diamonds on velvet. They were surrounded by strange, fuzzy halos. They looked like streetlights seen through a fogged windshield. At first, the engineers assumed it was a calibration error, a matter of focusing the secondary mirror or adjusting the fine guidance sensors. They sent commands to twitch the mirrors, to tweak the alignment, believing that the perfect focus was just a millimeter away. Days turned into weeks, and the image did not sharpen. The fuzzy halos remained, stubborn and inexplicable. The realization began to dawn slowly, dreadfully, that the problem was not in the adjustment, but in the glass itself. The telescope was suffering from spherical aberration. It is a term from optics that describes a mismatch in the way light reflects off different parts of a mirror. In a perfect mirror, light hitting the edges and light hitting the center should all converge at a single, precise focal point. In Hubble's mirror, the light from the edges was landing just slightly behind the light from the center. The rays were not meeting. Instead of a tight point, they created a blur. The telescope, the most expensive and sophisticated eye ever built, was nearsighted. The magnitude of the error was heartbreakingly small. The mirror had been ground to the wrong shape by roughly 2 microns, a fraction of the width of a human hair. It was a mistake so minute that on Earth it would be invisible to the touch, smoother than the finest polished marble. Yet, in the optical precision required for space astronomy, it was a catastrophe. The mirror was incredibly smooth. It was just smoothly wrong. It had been polished with exquisite care into the incorrect curve. The perfection of the surface only served to ensure that the error was perfectly uniform. The tragedy lay in the irony. The mirror was a masterpiece of craftsmanship, flawed by a simple measurement error during its creation, an error that had gone undetected until the instrument was floating 340 miles above the ground. The impact on the mission was immediate and devastating. The telescope had been sold to the world and the scientific community as a time machine capable of seeing the faint, distant galaxies formed shortly after the Big Bang, but the spherical aberration hit the telescope exactly where it hurt the most. The fuzzy halo effect scattered the light of faint objects, smearing it out until it blended with the background noise of space. The bright objects nearby, stars, planets within our solar system, could still be studied with computer enhancement, but the deep dark universe was lost. The faint whispers of light from the edge of time were drowned out by the telescope's own optical confusion. The primary goal of the mission, the very reason for leaving the atmosphere, had been compromised. The reaction on Earth was a mixture of scientific despair and public ridicule. The telescope, which had been heralded as a triumph of American ingenuity, became a punchline. It was the techno-turkey, a billion-dollar paperweight orbiting the planet. Cartoons depicted it wearing thick glasses. Editorials questioned the competence of the space agency. For the astronomers who had spent their careers preparing for this data, the grief was personal. They had waited decades for a view that was now denied to them. They were like composers who had written a symphony for an orchestra that had lost its instruments. The data was coming down, but it was compromised, a blurry shadow of the potential they knew existed. Yet, within the failure lay a strange resilience. The telescope was wounded, but it was not dead. It was still a functioning spacecraft, stable and communicative. The engineers refused to accept the situation as a total loss. They began to work with what they had, developing complex algorithms to mathematically subtract the blur from the images. It was a digital form of squinting. They could sharpen the pictures of bright objects, squeezing valuable science out of the flawed instrument. But they knew this was a stopgap. Software could not recover light that had been scattered away. To truly fix the problem, they had to confront the physical reality of the mirror. The realization that the ketoscope was flawed forced a profound shift in perspective. Until that moment, space exploration had often been framed as a conquest of distance and power. We built rockets to go fast. We built probes to go far. The Hubble failure brought the challenge back to the intimate scale of human error. It wasn't a meteor strike or a solar flare that had blinded the observatory. It was a speck of dust on a measuring rod, a misinterpreted test result in a clean room on Earth. It was a reminder that no matter how far we send our machines, they carry our imperfections with them. We cannot escape our own fallibility by leaving the planet. The flaw in the mirror was a mirror of ourselves, ambitious, capable of brilliance, but prone to simple, overlooked mistakes. The conversation shifted from what went wrong to what can be done. The mirror itself could not be replaced. It was the heart of the telescope, buried deep inside the structure, impossible to swap out in orbit. Bringing the telescope back to Earth to fix it would be prohibitively expensive and risky, potentially grounding it forever. The solution had to be applied in space. This constraint sparked one of the most creative periods in the history of engineering. If they couldn't change the eye, perhaps they could give it spectacles. The problem was optical, a known mathematical deviation. Therefore, the solution could also be optical. If they could introduce a new set of mirrors into the light path, mirrors ground with the exact inverse of the error, they could cancel out the aberration. They could correct the vision before the light hit the cameras. But this was a theory. Turning it into reality required a level of audacity that bordered on the reckless. It meant building a corrective instrument, device the size of a telephone booth, and launching it on a shuttle. It meant sending 7 astronauts to catch the telescope with a robotic arm, hold it steady, and perform the most complex surgery ever attempted in the vacuum of space. They would have to open the telescope's doors, remove a large instrument to make room, and install the new corrective optics with the precision of a watchmaker, all while wearing bulky pressurized gloves and floating in zero gravity. The stakes were absolute. If the repair mission failed, the Hubble would remain a symbol of failure, a drifting monument to wasted potential. It would likely end the era of large space telescopes before it had truly begun. If they touched the wrong wire, stripped a bolt, or bumped a mirror, they could turn a nearsighted telescope into a blind one. The mission was not just about fixing a machine. It was about redeeming the reputation of science itself. It was about proving that human ingenuity was not just about building perfect things, but about recovering when perfection failed. As the repair mission was prepared, the telescope continued to orbit, dutifully sending down its blurry pictures. It watched the universe through a haze, a lonely sentinel waiting for a cure. The astronomers on the ground learned to be patient. They learned to look at the fuzzy images and see the structure hidden within the blur. They prepared their proposals for the time when the vision would be clear. The failure had taught them humility, but it had not killed their curiosity. The darkness was still there, waiting to be seen. The error had merely postponed the revelation, adding a chapter of struggle to the story of discovery. The telescope was not just a camera anymore. It was a character in a drama, a flawed protagonist waiting for redemption. With the vision of the telescope restored, the scientific world breathed a collective sigh of relief. The corrective optics had worked, transforming the fuzzy, nearsighted halos into points of diamond-hard clarity. The machine was finally the instrument it was promised to be. Immediately, the pressure to use it intensified. The queue of astronomers waiting for time on the Hubble was long and impatient. They had spent years preparing proposals, calculating the precise orbits of moons and the spectral signatures of distant quasars, waiting for their turn to control the most powerful eye in history. The schedule was packed with specific known targets: a storm on Saturn, a dying star in the Orion Nebula, a jet of gas firing from a black hole. These were the celebrities of the night sky, the objects we knew were there and desperately wanted to see in detail. In the midst of this rush to observe the known, a quiet, counterintuitive plan began to form in the office of the Space Telescope Science Institute. The director, Robert Williams, possessed a unique privilege known as Director's Discretionary Time. This was a small percentage of the telescope's schedule set aside for projects that did not need to pass through the rigorous, often conservative, peer review process. Usually, this time was used to chase sudden events, supernova exploding overnight, or a comet unexpectedly brightening. But Williams had a different ambition. He did not want to look at an event. He wanted to look at a void. He proposed aiming the telescope at a patch of sky that ground-based surveys had declared to be completely empty, and simply holding it there. The proposal was radical because it violated the fundamental rhythm of modern science. Research is typically hypothesis-driven. An astronomer observes a phenomenon, forms a theory, and then requests telescope time to prove or disprove it. You point the camera because you expect to see something specific. Williams' plan was the opposite. It was discovery-driven. He wanted to point the camera specifically because he did not know what was there. He proposed to stare into the nothingness for 10 consecutive days in eternity, in the high-speed economy of spaceflight, just to see if anything was hiding in the dark dot. The risk involved in this decision cannot be overstated. The Hubble Space Telescope is a finite resource. It orbits the Earth every 97 minutes, and every second of that orbit is accounted for, costed, and fought over. To dedicate hundreds of orbits, over 100 hours of exposure time to a single blank spot was viewed by many in the community as a reckless gamble. If the image came back black, it would be a public relations disaster for an agency that had just barely recovered from the mirror embarrassment. It would be seen as a waste of a billion-dollar asset. There was no guarantee that the camera would see anything other than the faint, grainy static of the electronic background. It was a wager of time against the unknown. With the reputation of the observatory placed squarely on the table, the first challenge was not capturing the image, but choosing the right kind of nothing. It sounds simple to find a dark spot in the sky, but for a telescope of this sensitivity, the sky is cluttered with local debris. The team had to thread a needle through the layers of our own celestial neighborhood. They could not point anywhere near the sun, for obvious reasons. But they also had to avoid the moon and the Earth's bright limb. More difficult was avoiding the zodiacal light, the faint glowing fog of dust that fills our solar system, scattering sunlight and creating a permanent haze in certain directions. This local dust would act like a dirty window, washing out the ultra-faint signals from the deep universe. Beyond our solar system lay the next hurdle, the Milky Way itself. We live inside a galaxy, a flattened disk filled with billions of stars and thick clouds of interstellar gas. When we look up at the night sky and see the band of the Milky Way, we are looking into the crowded plane of our own home. To see the deep universe, the telescope had to look away from this plane. It had to look up or down relative to the galactic disk, peering out through the thinnest part of the galaxy's atmosphere, like a person in a crowded stadium trying to see the sky by looking straight up through the open roof. If the telescope pointed even slightly toward the galactic center, the image would be choked with thousands of foreground stars, bright points of light that would burn out the sensors and hide the distant galaxies behind them. The search for the perfect keyhole became a rigorous process of elimination. The team scanned star charts and digital surveys, looking for a region that was boring. They needed a spot with no bright naked-eye stars, no known clusters, no radio sources, and no infrared heat signatures. They needed a high galactic latitude to escape the Milky Way's dust. They needed a spot that the telescope could view continuously without being blocked by the Earth during its orbit. After weeks of searching, they found a candidate. It was a tiny, nondescript patch of sky in the constellation Ursa Major, just above the handle of the Big Dipper. To the casual observer, this region is utterly unremarkable. It is a blank space between the stars that form the familiar shapes of the constellations. It covers an area of the sky roughly equivalent to a grain of sand held at arm's length against the dark. If you were to stand in a dark field and look up at it with the finest pair of binoculars, you would see absolutely nothing. Even the powerful ground-based telescopes of the time saw only a few faint smudges. It was, for all intents and purposes, a dead zone, and that is exactly why it was chosen. The lack of foreground distractions meant that if the telescope saw anything, it would have to be incredibly far away. By selecting the emptiest direction, they were ensuring that the view would be deep. The philosophy behind this choice was akin to drilling a core sample in geology. When a geologist wants to understand the history of the Earth, they do not dig in a busy city or a shifting riverbed. They go to the ice sheets of Antarctica or the sediment of the deep ocean floor, places where the layers have settled undisturbed for eons. They drill a narrow vertical shaft, pulling up a cylinder of material that reveals the timeline of the past. The deep field, as the project came to be called, was a core sample of the universe. The narrow field of view would act as the drill, boring a tunnel through the emptiness of space to reveal the strata of cosmic history. This method of observation required a shift in how we think about seeing. In our daily lives, seeing is instantaneous. We look, and the image is there. But in astronomy, seeing is cumulative. It is an act of gathering. The faint photons from the edge of the universe arrive at Earth, one by one, like raindrops falling in a drought. To build an image, the telescope must act like a bucket, sitting out in the rain for a long time, collecting every stray drop. The fainter the object, the longer the bucket must sit. The plan called for the Hubble to stare at this single grain of sand for 10 days, accumulating light over hundreds of separate exposures. This requirement for a long stare imposed a terrifying technical demand on the spacecraft. The telescope orbits the Earth at 17,000 miles per hour. It is subjected to the thermal shock of passing from sunlight into shadow every 45 minutes, causing its metal structure to expand and contract. It feels the drag of the thin upper atmosphere and the gravitational tug of the moon. Yet, to capture the image, it had to keep its gaze locked on that specific patch of sky with the stability of a laser, pointer held steady in the dark 200 miles away. If the telescope jittered by even a fraction of a degree, the image would blur, and the faint light would be smeared out and lost. The team prepared the commands, uploading the sequence to the onboard computer. The decision was made. They were going to spend the most valuable scientific currency on Earth to look at a blank wall. There was no fanfare, no countdown broadcast to the public. It was a quiet command, sent from a control room in Maryland, to a robot floating in silence. The telescope slewed its massive body. The gyroscopes worried to arrest its momentum. The aperture door was open. The sensors were chilled. The target, the emptiness near the Big Dipper, was centered. The question was no longer about the hardware. It was about the universe itself. Was the darkness truly empty, or was it merely waiting for someone with the patience to really look? The observation ended as quietly as it had begun. The telescope, having stared at the same speck of darkness for 10 days, finally received a new command. It slewed away, its gyroscopes humming as they reoriented the massive vessel toward a new target, perhaps a bright planet or a nearby nebula, leaving the patch of Ursa Major behind. In the cold vacuum of orbit, nothing had changed. The region of sky looked exactly as it had before, a blank, impenetrable wall of night. But inside the onboard memory banks of the spacecraft, something new existed. A ghost had been caught in the machine. The accumulated light of 100 hours was now stored as a stream of binary code, waiting to be beamed down to the receiving stations on Earth. The transmission of this data was not an instantaneous revelation. It did not arrive as a finished photograph that slid out of a printer. It came in fragments, a digital mosaic scattered across time and radio frequencies. The signals were caught by giant dish antennas in New Mexico and Australia, then piped through cables to the Space Telescope Science Institute in Maryland. There, the data entered the quiet humdrum world of servers and monitors. It is a strange contrast that the most profound secrets of the cosmos are often revealed, not in the dramatic setting of an observatory dome open to the night air, but in the fluorescently lit rooms of data processing centers, where the only sound is the whir of cooling fans and the clicking of keyboards. For the astronomers waiting at the terminals, the initial look at the raw files was an exercise in faith. The individual exposures were unimpressive. A single frame, representing just a portion of the total exposure time, looked grainy and washed out. It was riddled with noise, the electronic static of the camera itself, and peppered with bright, jagged streaks caused by cosmic rays. These high-energy particles, whizzing through space, strike the telescope's detectors constantly, leaving false scars of light on the image. To the untrained eye, the raw data looked like a ruined photograph, a snowy television screen with no clear picture. It required a disciplined mind to look at this mess and know that buried underneath the static, the universe was waiting. The process of revealing the image was akin to an archaeological excavation performed with mathematics. The team began the laborious work of cleaning the data. They had to stack the hundreds of separate images on top of one another, aligning them with perfect precision. This technique, known as drizzling, allowed them to preserve the finest details while averaging out the flaws. Because cosmic rays strike randomly, they appear in different spots on different frames. By comparing the stack, the computer could identify these transient streaks and remove them, leaving only the permanent light, the light that had actually come from the sky. As the stacking continued, the image began to deepen. It was a slow development, like a Polaroid fading into view, but infinitely more subtle. With every layer added, the background noise receded, the graininess smoothed out, and the true signal rose above the floor of static. The grey fog of the raw data darkened into a true black, and out of that black, shapes began to materialize. They did not appear with a flash, but with a steady, relentless persistence. They were there because they had always been there, burning quietly in the dark, waiting for a bucket large enough to catch their rain. When the final composite was assembled, the result was a shock to the system. The screen, which should have been mostly empty, was full. It was not just occupied, it was crowded. The black square of the empty sky was densely packed with objects. Wherever the eye looked, there was something. It was a tapestry of light, scattered like jewels across black velvet. The density was disorienting. The team had expected to find perhaps a few dozen faint galaxies, lonely outposts in the void. Instead, they were looking at thousands. In a patch of sky the size of a grain of sand, the telescope had found an entire metropolis of structures. The most immediate realization was the lack of stars. In almost every other photograph of the night sky taken from Earth, the foreground is dominated by the stars of our own Milky Way, bright, spiky points of light that sit on top of the background. But here, because they had chosen the keyhole so carefully, there were almost no stars. There were less than a dozen foreground points in the entire image. Everything else, every smudge, every spiral, every dot was a galaxy. Each of those tiny points of light was not a single sun, but a city of billions of suns. The image had punched a hole through the screen of our local reality and looked directly into the deep ocean beyond. The visual variety of the objects was staggering. The universe, it turned out, was not a uniform sea of identical shapes. The image was a chaotic gallery of forms. There were the majestic, grand spirals, like our own Milky Way and Andromeda, turning in serene pinwheel perfection. These were the mature galaxies, the settled empires of the cosmos. But they were the minority. Surrounding them were thousands of other shape-ragged fragments, strange cigars of light, tadpoles with long tails, and shapeless blobs of blue and red. It looked less like a formal portrait and more like a candid snapshot of a busy crowd. There was a sense of motion and interaction, a frozen record of a dynamic, churning history. The colors, too, told a story that the eye had to learn to read. The image was not monochrome. It was a composite of red, blue, and green light, representing physical truths about the objects. The blue objects were ablaze with the fierce light of hot, young stars, stellar nurseries where creation was happening violently and quickly. The red objects were different. Some were old, filled with dying stars that had cooled to a sunset glow. But others were red for a different reason, a reason that touched on the very architecture of space and time. They were red because they were far away. The expansion of the universe had stretched their light as it traveled, shifting it toward the red end of the spectrum. These were the ancient signals, the whispers from the edge of the visible horizon. The sheer depth of the field created a sense of vertigo for those who understood what they were seeing. In a normal photograph, objects are usually at roughly the same distance: a landscape, a group of people, a bowl of fruit. But the deep field was a tunnel. The large, bright galaxies were the nearby ones, perhaps only a billion light-years away. The smaller ones were behind them, and the tiny, faint dots were behind those. The image was a core sample of time. Looking at the picture was like looking down a well. The farther down you looked, the further back in history you went. The smallest specks of light were photons that had started their journey when the Earth was nothing but dust. They were the baby pictures of the universe, arriving at the end of their lives to be caught by a mirror in low Earth orbit. The emotional impact of the image lay in its contradiction. It was a picture of a tiny, insignificant patch of nothing, and yet it contained everything. It forced a recalibration of the word empty. If you could take a sewing needle and hold it at arm's length, the eye of that needle would cover the area of sky this image represented, and in that tiny eye there were 3,000 galaxies. If you extrapolated that density to the entire sky, if you assumed that every patch of darkness was as full as this one, the math became overwhelming. The universe was not a lonely place with vast distances between islands of light. It was a saturated environment. The darkness was not an absence of material, it was merely an absence of sensitivity. The stuff of the universe was everywhere, layered deep into the dark, hidden only by the limitations of our vision. As the scientists zoomed in on the high-resolution files, panning across this digital sky, the feeling was one of intrusion. It felt as though they were peeking into a private room of the cosmos, a place that had never been meant for human eyes. These galaxies had lived their entire life cycles, spinning, colliding, birthing stars, and dying in absolute seclusion. No eye had ever registered their existence. Their light had washed over the Earth for billions of years, unseen by dinosaurs, by early hominids, by the great astronomers of the Renaissance. They had been phantom signals, raining down on a blind planet. Now, for the first time, the loop was closed. The light had found a receiver. The silence of that specific patch of sky had finally been broken, not by sound, but by witnessing. When the human mind attempts to measure the world, it instinctively seeks boundaries. We look for the edge of the forest, the shoreline of the sea, or the walls of a room. We find comfort in knowing where things end. But the image returned from the dark patch in Ursa Major offered no such comfort. Instead of finding a limit, the telescope revealed a depth that seemed to have no bottom. The most immediate implication of the deep field was a radical revision of the census. Before this long stare, astronomers had estimated the population of the cosmos based on the brighter, nearby neighborhoods we could see from Earth. We assumed the density of the universe was somewhat consistent, a scattering of galaxies separated by immense, sterile voids. But the deep field shattered this assumption. It showed that the universe was not merely populated, it was saturated. If one were to take that single grain of sand held at arm's length, a tiny fraction of sky covered by the image, and count the 3,000 galaxies within it, the mathematics of extrapolation becomes staggering. Since there is nothing special about that specific patch of sky, we must assume it is representative of the whole. If every grain-sized patch of the celestial sphere contains 3,000 galaxies, then the total number of galaxies in the observable universe is not in the millions, but in the billions. The estimate jumped overnight to over 100 billion galaxies. Each of these is not a star, but a system of stars, an island containing hundreds of billions of suns. The mental arithmetic required to hold this number is almost impossible. The universe suddenly became a place of overwhelming quantity, where the sheer amount of matter defied the human capacity to imagine it. However, to count the galaxies is to miss the deeper truth of the image. This was not merely a map of where things are, it was a record of when things were. The photograph is a deception of two dimensions. It presents all the objects as if they are sitting on the same flat surface, painted on a canvas of black. But this flatness is an illusion. The image is actually a deep, vertical shaft through time. Because light takes time to travel, the objects in the image are not contemporaries. They do not exist in the same now. The large, bright spirals are the nearby neighbors, seen as they were perhaps a few 100 million years ago. But the smaller, fainter smudges are billions of years in the past. To look at the image is to look down a long corridor of history, seeing the universe at different stages of its life simultaneously. This realization transforms the deep field from a picture into a timeline. It allows us to do something that is impossible in human biology. We can see our own ancestors. In the natural world, we cannot look at a living adult and simultaneously see them as a child and as an infant. The past is gone, replaced by the present. But in astronomy, the past is still arriving. The faint red specks in the background of the image are the infants of the galaxy world. They are the structures as they appeared when the universe was less than 1 billion years old. By studying them, we are looking at the era of construction, the time when the lights were first turning on. The universe we see in the background is not the same as the universe we inhabit in the foreground. It is a younger, wilder, and more compact place. The visual evidence of this evolution is striking. The galaxies in the local universe, the ones near us in space and time, are often majestic and orderly. We see grand spirals with well-defined arms, like our Milky Way, or massive glowing spheres known as ellipses. They look stable, settled, and mature. But as we peer deeper into the image, back into the remote past, the shapes change, the order dissolves. The distant galaxies are not stately spirals. They are wrecks, they are jagged fragments, shapeless lumps, and distorted trains of light. They look unfinished. This creates a profound narrative arc. We are witnessing the physical evolution of structure itself. We are seeing the universe before it organized itself into the elegant forms. We know today that this chaotic background tells us that the early universe was a violent construction site. The empty space was filled with the debris of creation. We see galaxies in the process of colliding, tearing each other apart with gravity, and merging to form larger structures. It suggests that the majestic galaxies of today were built from the ruin of these earlier, smaller blocks. They grew by consuming their neighbors. The deep field captures these mergers in progress, frozen by the delay of light. We see two galaxies passing through each other, their stars thrown out into long tidal tails, locked in a gravitational dance that will take millions of years to resolve. To us, it is a static picture, but in reality, it is a snapshot of a kinetic, aggressive history. The thickness of the universe, therefore, is not just a matter of object density, but of temporal density. The light from these different eras is stacking up, layer upon layer, on its way to Earth. A photon from a nearby star might arrive at the telescope at the exact same moment as a photon that has been traveling for 10 billion years. They hit the detector together, mingling their signals. The night sky is a choir where the voices of the ancient dead are singing in harmony with the voices of the living. Disentangling them requires us to sort the light by its age, to push the now aside to see the then. It reveals a universe that has never stopped changing, a restless organism that has evolved from a soup of small, blue fragments into a cosmos of giant, isolated islands. The colors in the image provide the code for this sorting. As the universe expands, it stretches the space between galaxies. This stretching affects the light traveling through it. A wave of blue light, emitted by a hot young star in the distant universe, is pulled apart as it travels across the expanding void. By the time it reaches us, the wave has been lengthened, shifting its color from blue to red. This phenomenon, known as redshift, acts as a cosmic odometer. The redder the object, the farther it has traveled, and the older it is. The deep field is filled with these red dropouts, galaxies that have almost faded from view. Their light stretched to the very limit of what the telescope can detect. These are the sentinels of the dawn, marking the era when the fog of the beginning first cleared. Seeing these ancient objects forces a confrontation with the concept of origins. For centuries, the question of how the universe began was the domain of theology or philosophy. It was a story told in myths. But here, in a patch of sky the size of a grain of sand, the answer was presented as data. We could measure the size of the galaxies when they were young. We could count the rate at which they were forming stars. We could see that the universe was hotter and busier in the past than it is today. The darkness was not just filled with matter, it was filled with the energy of a billion births. The star formation rates, the heartbeat of the cosmos, was much faster in those early epochs. The universe was blazing with a productivity that has since slowed down. We are living in the quiet afternoon of the cosmos. The deep field looks back at the frantic activity of the morning. This perspective shifts our understanding of our own place in the story. We often feel that we are looking out at a universe that is alien and separate from us. But the heavy elements in our bodies, the carbon in our cells, the iron in our blood, were forged in the generations of stars that burned and died in those distant, ragged galaxies. The thick, crowded history revealed in the image is our history. The chaotic mergers and the violent starbursts of the deep past were the necessary precursors to the calm stability of our solar system. The nothing that we thought we were looking at turned out to be the family album of matter itself, a dense record of the events that allowed complexity to emerge from the void. The image that returned from the darkness did more than just fill a gap in our maps. It dismantled a fundamental intuition about our place in the reality of things. For as long as humans have looked up, the night sky has been defined by its blackness. The stars were precious because they were rare. They were scattered diamonds on a vast velvet cloth, and the cloth was understood to be the primary substance of the universe, a great, encompassing nothingness. We built our philosophies and our mythologies around this contrast, the light against the dark, the being against the non-being. But the deep field image quietly erased this distinction. It proved that the blackness was not empty, it was merely deep. It showed us that if our eyes were powerful enough, the sky would not be dark at all. It would be a blazing, solid sheet of galaxies, overlapping each other in a continuous tapestry of light, extending to the beginning of time. This realization forces a profound psychological shift, a kind of vertigo that is less about height and more about significance. We are accustomed to being the protagonists of the story. Our sun is the center of our solar system. Our galaxy is the bright, churning home that dominates the night. We naturally assume that we are located in a region of importance. But when we look at the deep field, we are confronted with the crushing homogeneity of the cosmos. The patch of sky we examined was chosen specifically because it was ordinary. It was a random sample, and yet it contained a universe of complexity equal to our own. This implies that there are no special places. Every direction we look, if we look deep enough, reveals the same overwhelming richness. We are not standing in a clearing in the forest. We are lost in the middle of an endless thicket, where every tree looks like every other tree, and the forest goes on forever. There is a specific kind of silence that accompanies this knowledge. It is the silence of the ego receding. When we believed the universe was small, we could imagine that it was made for us. When we believed it was mostly empty, we could imagine that life was a singular, miraculous accident. But when we are faced with 100 billion galaxies, each containing 100 billion stars, the claim of exclusivity becomes harder to hold. The sheer statistical weight of the image presses down on our sense of uniqueness. It suggests that the processes that created us, the fusion of elements, the formation of planets, the chemistry of life, are likely happening everywhere, all the time, in every corner of that grain-sized patch of sky. We are not the lonely inhabitants of a desert. We are merely one voice in a choir so large that we cannot hear the other singers. This shift in perspective redefines the act of seeing. We often think of vision as a tool for navigation, a way to avoid obstacles and find what we need. But the deep field demonstrates that true seeing is an act of accumulation. It requires a surrender of the impulse to glance and move on. The universe does not reveal itself to the impatient. The photons from the edge of time are weak and scarce. They cannot compete with the noise of the immediate present. To catch them, we must stop moving. We must hold our ground and keep our eyes open long after the brain says there is nothing there. This is a lesson that extends beyond astronomy. It suggests that the superficial view of reality is almost always wrong. The surface is a mask. The depth is where the truth resides. But the depth requires a commitment of time that modern life rarely permits. The image also challenges our concept of the void. We have spent centuries fearing the vacuum, treating space as a hostile, sterile environment that separates worlds. We treat the distance between stars as a barrier, but the deep field suggests that the void is actually a connector. It is the clear medium that allows the history of the universe to survive. If space were not empty, if it were filled with dust or fog, the light from those distant galaxies would never reach us. We would be trapped in a cosmic fog, unable to see beyond our own backyard. The transparency of the universe is what allows us to know it. The nothingness is the very quality that grants us access to the everything. The darkness is not a wall, it is a window. As we stare at the myriad shapes in the image, the spirals, the ellipses, the train wrecks of colliding galaxies, we are also forced to confront the scale of our ignorance. Before this image was taken, we did not know these galaxies existed. They were completely absent from human knowledge. Yet, they were there, churning and evolving, for billions of years. This brings up the unsettling question: what else is staring us in the face, invisible only because we have not yet built the right machine to see it? The deep field is a reminder that reality is not limited by our perception. The universe does not cease to exist when we close our eyes. It is vast, indifferent, and busy, regardless of whether we are watching. We are late arrivals to the party, walking into a room that has been full of conversation for eons. This humility is perhaps the most valuable product of the Space Telescope. The scientific data is crucial: the expansion rates, the star formation histories, the chemical compositions. But the cultural impact is heavier. The image serves as a corrective to the human tendency to focus on the immediate and the local. We worry about our daily lives, our politics, our borders, and our differences. These things feel immense because they are close. But when placed against the backdrop of the deep field, they vanish. The entire Earth, with all its history and conflict, would not even register as a single pixel in one of the thousands of galaxies in that image. It is a perspective that is terrifying in its scale, but also strangely liberating. It lifts the weight of self-importance and replaces it with the lighter sensation of belonging to something infinite. The decision to look at nothing was, in retrospect, an act of supreme optimism. It was a declaration of faith in the richness of the universe. It assumed that if we asked the question, the cosmos would have an answer, and the answer was louder than anyone expected. It told us that the universe is not stingy. It is extravagant. It does not sprinkle matter sparingly. It pours it out. It creates structure with a relentless drive that seems built into the laws of physics. To look at the deep field, is to see the result of a creative force that has been operating without pause for 14 billion years. It is a picture of an engine that never sleeps. Ultimately, the story of the telescope and the dark patch of sky is a story about the maturation of the human species. A child thinks the world ends at the garden fence. An adult knows there is a wider world, but focuses on their own street. A philosopher knows the street is just one path in a city, but the astronomer knows the city is just one speck of dust in a storm. We are slowly, painfully, learning to accept our true size. We are learning that we are small, but we are also learning that being small is not the same as being insignificant. Being small allows us to be observers. It allows us to stand on the shore of the cosmic ocean and appreciate the view, to witness the grandeur without needing to control it. The deep field did not give us new lands to conquer. It gave us a new way to be.